start with energy. How would you describe energy? There's a very mathematical way of approaching energy, and there's a very conceptual way of approaching energy. Let's start with approaching it conceptually. How would you describe energy?
Adenosine triphosphate.
Adenine triphosphate, ATP, muscle energy. The most efficient way of converting glucose or sugar, something like that, into oxygen, something like that. I don't know. It's been a while since I took AP Bios.
Calvin cycle.
Calvin cycles. Just throw some words out there. Okay. So we can still go off of that too. I mean, when we talk about chemical reactions in your body to get energy, quote unquote, what does it mean to get energy? What does that do? What is
about phosphorylating the ATP? And
okay, but what's the outcome of that? What do you get out of it? Chemical energy. But what is okay? So what does that do? What do you get out of that? You can do some things. Great. The ability to cause change, something along those lines. Any other kind of? I'm looking for something more general, right? Ability to cause change. Andrew. Okay, the ability to do work. So let's start with a couple of those definitions. Because, again, the textbook will kind of have a pretty technical definition, and especially when it comes to energy, it can really help to have a real-world connection, kind of intuitive understanding of what we're talking about here when we talk about energy. So I'll put in parentheses as I'm quoting you guys. The ability to cause change. Or the ability to do work. Yesh, what was it? You said you said something too. What was it? No, I don't remember. Something along those lines. Okay. Okay. The ability to cause change or the ability to do work. We'll come back to the doing work part because we'll find that work has a very specific mathematical meaning when it comes to physics, and it's not just, expending energy. Okay, it's not just expending energy. So, okay, the ability to cause change. So anything from causing a chemical reaction to causing a nuclear reaction to pushing and pulling on something and causing it to move, right? So on and so forth. Okay, so it can kind of help to categorize the different kinds of energy that we generally put things into categories. Just like when we did forces, we have normal force and all that kind of stuff. We can kind of do that with energy too. So what are the different kinds of energy that you know about? Cool. Kinetic, potential. Kinetic, potential. What else? Chemical. So we'll put kind of chemical under potential because you have chemical potential energy. Okay, thermal energy. What else? Trying to see what you guys already know here. Background knowledge. Chris. Nuclear energy? That's what you said, right? Nuclear. Okay. Yep, energy. Mechanical energy. Okay, so let's put that. Okay, I'll put that right here. But you'll see that there's a little bit of overlap because kinetic energy would count as mechanical energy. What else? Gravitational energy, maybe a gravitational potential. Okay, good. I mean, we'll explore these a little more, but yeah, gravitational potential energy. What else? It's funny because I just did this exact same activity with my freshman students. We're doing energy too. But we haven't done forces. So. What else?
It's light energy thing.
Light energy. I will call that electromagnetic energy. Elastic. Cool. I will put that here. Because elastic energy is also a potential energy. You can only store it. Yep. Sound. Yes. I'm trying to think of. I will call it wave energy. And that is a mechanical energy. Okay. Doesn't necessarily have to be sound. It could be ocean waves. It could be any kind of wave. It is not exactly kinetic energy. It's an energy in an organized motion of particles. It's a little different. So wave energy, good. Awesome. What else? Is there anything else? Dark energy? We will leave that to, maybe we'll figure it out 100 years from now. Okay, I think that's a pretty good list. If you guys can come up with something else as we're going, we'll throw it on there. So now the question is, figuring out what they all mean. Okay, let's actually get some definitions on here. So, kinetic energy. So what is kinetic energy?
Energy of movement.
Perfect. Energy of movement. Thank you, Steve.
Steven.
Sorry. Not Steve. Jeremy. Sorry, he was just a very memorable guy.
Yes, he was.
Energy of motion. Good. How about any questions about kinetic energy? So let's do this. It's actually I've been finding it kind of interesting how I'm able to do notes in my freshman class because I can force them to all do Avid notes or the Cornell notes, and you guys don't do Cornell notes. So the structure of this is a little tricky, how you do your notes. But somewhere in here, I want you to try and think of an example of kinetic energy. It can be super simple. Give me an example of kinetic energy. Sure. A domino falling. Perfect. That's fine. Because the thing is, it's a complex scenario. So you can actually apply a variety of different energies that are going on there, right? So, parentheses, domino falling. Okay. Is the falling part, is the moving part, right? The moving part, that's where the kinetic energy is. Okay. I want to follow that up with gravitational potential energy. Okay, gravitational potential energy. So what is gravitational potential energy? If I put those two words together, really just thinking about potential energy, we usually think of potential energy as like a stored energy. So you have like electrochemical potential energy in a battery, or you can have just electric potential energy in a capacitor. There's all these different ways to, or elastic potential energy, right? When you stretch a rubber band, it's storing energy. So what would gravitational potential energy be? Yeah. Yeah, just lifting something up. That would be a perfect example of it. So as you lift something up, you are storing gravitational potential energy pretty much just because it wants to fall, right? So you can kind of describe it like this. It is an energy, energy associated with the vertical position, is an energy associated with the vertical position of an object influenced by gravity. This one's going to be very important because eventually what we'll see is that we can kind of treat gravity in a very visual way. We call it a gravitational field. And when an object is in a gravitational field, there's mathematical ways of describing how it's influenced by that field. And it turns out that there's another phenomenon that acts very much like a field, which is the electric field. And so then you can also have an electric potential energy. They both behave very similarly. Okay, they both behave very similarly. So this will be a useful parallel. So for this example, you could say like lifting something. L-I-F. Or you could also say domino falling. the perfect example for everything. Okay, cool. So how about now some of these? I'll be honest. You don't need to know some of these or at all for AP Physics exam. Okay, but that's not the point. I think for me to feel comfortable saying you took a rigorous physics course, I think it's important that you should be able to distinguish between these different kinds of energy because, well, they're really important. So how about chemical potential energy? Who's taking AP Chem? So what's chemical potential energy?
It's energy that's stored in the bonds between molecules.
Perfect. Okay. Energy stored in the bonds between molecules. Sometimes you can release energy or store energy, not necessarily breaking bonds, but also forming bonds, right?
Right.
So it's not necessarily just, I guess we have to take both into account. Okay, so maybe you can say both. Energy stored in the forming or breaking of energy stored in the forming or breaking of chemical bonds. That's one way to put it. I want to dig a little deeper on that. Why do chemicals form bonds at all? Like ionic bonds. Why are they formed? Yeah, Andrew.
To satisfy the octet rule.
Okay, why does it want to satisfy the octet rule?
Like stable.
Okay, stability. Okay, so it is kind of like a minimum energy state for each of the elements, right? So even when you look at covalent bonds or ionic bonds, and you look at the electronegativity of different elements, the idea is that there is a minimum energy state of or organization of the electrons. So if you want to focus more on just thinking about the electrons, when we talk about chemical bonds, it's important to note that all chemical bonds only have to deal with electrons, right? You never talk about protons jumping over to another atom, right? That's a nuclear reaction. So, okay, so energy stored in forming or breaking of chemical bonds. I just kind of leave that, a little asterisk there because I want you to think about the electrons. Yep, Ben. Yes. Let's put that here. Electrical potential energy. I know I left that space for a reason. Cool. Examples of chemical potential energy. How about eating food? Right? That's chemical potential energy. Or fuel in your car, internal combustion engines, yada yada, right? Cool. How about, we're kind of hitting all the potential energies here. How about elastic potential energy? How would you describe? Yep.
Isn't it something like a spring?
Yeah, it doesn't really have to be a spring though, right? Because if I take this ruler, this meter stick, and I bend it like this, you can clearly tell there is a potential energy stored. There's energy stored here. There's energy stored here. If I really bend it and it breaks, right, it will release a lot of energy. Okay, so it doesn't necessarily have to be from a spring, from like, you know, whatever it is. So there's something more general about what is the cause of elastic potential energy. How would you describe it?
The want for an object to return to its relaxed state.
Okay, so what makes it unrelaxed? Okay, so the bonds are being stretched when we, a couple of words that you could use here, you deflect it, you strain it. Excuse me. The more technical term is that you strain it. Strain is a deformation of the shape, right? So I can, this ceramic tabletop, I can press on it as hard as I want. Most ceramics don't really have a elastic potential energy, right? They don't really displace. They don't change shape. Ceramics are very brittle, but they're also very hard. So they don't generally change shape. They're either of a certain shape, they don't really store the energy, and then they break, right? And then they break. As opposed to like something like this wood, you know, fibers, carbon fibers, things like that, they tend to change shape but go back to their original shape, right? So I'll put it this way: it is an energy stored in the strain / deformation of an object. Okay, so of course you can use a spring, but if you think about, you know, what is it that a spring really does? You take a bunch of wire and you coil it around, right? And so it's really just the kind of behavior and shape of the metal that allows it to want to go back to its original state. And so then that's how it can store energy. Okay, how about electrical potential energy? Actually, I'll just call it electric potential energy. How about electric potential energy? What is electric potential energy? How does lightning work? Okay, stored charges between the cloud and the earth. In other words, it's not just that you're storing charges, it's that you have an imbalance of charges, right? There's plenty of charges in the clouds right now, there's plenty of charges on the earth, but they're more or less neutral. It is when it's not neutral that you suddenly have electrons wanting to move towards protons, right? Or negative charges trying to go towards positive charges. So it is when you have a separation of charges, the more you separate them, or the more charges you have separated, the more potential energy you have that when you can release them, they'll want to come back together. So that's essentially what a battery does, right? A battery uses electrochemical reactions or chemical reactions to separate charges. You have more electrons on one side than the other, and you keep them separated. And then when you connect the two sides of a battery, they can now flow back and recover themselves. So let's see, energy stored in the separation of charges. Okay. This is maybe an example of that, lightning or something like that. Okay, that's it. Lightning's a decent example. Okay, how about thermal energy? What is thermal energy? Now, my freshmen were pretty bad at this, but I think if you took chem, you should know. You hear?
Is it like the energy that we feel from like heat or?
Okay, has something to do with heat. What is heat then?
Movement of molecules.
Movement of molecules, sort of. Okay, vibration. Got something like that. Anna, you were gonna say something?
I was going to say, was the energy released as heat?
Okay, energy released as heat. So, sort of. Okay, I think when we think of our everyday experiences with heat, we tend to think of it as, okay, something's hot or something's cold. Something feels hot, something feels cold. But what we're really feeling, we're not feeling the temperature of an object. We're feeling the energy transfer with that object. If something feels really cold, that means energy is transferring out of our body quickly, and our nerves experience that. Okay, me here.
So like if something is like hot, like a cup of coffee,
Mm-hmm.
and then it loses like that heat, is that thermal energy? It's losing thermal energy?
It's losing energy. It's losing energy. You could say it's losing thermal energy. Still trying to find a good way of defining what thermal energy really is. What makes something higher temperature than something else? What is it mechanically or of the property of the object that we're describing that's different when we say one object is 100 degrees Celsius and another object is 80 degrees Celsius? Yeah, energy. What's moving faster? Okay, the atoms. So when we talk about the temperature of an object, it really is the kind of the random motion of the molecules and atoms, right? So the higher the average kinetic energy of these different atoms and molecules on the inside, not the bulk movement, right? Kinetic energy is a bulk movement. I take my cup of coffee and I throw it out the window. That's kinetic energy. But if I just let it sit there, it has convection. It's moving. The molecules are just kind of shaking and moving around, right? So if that's a measure of temperature, then when you experience heat, heat is the transfer of that random kinetic energy. So if you really think about it at the microscopic level, at the atomic level, when you have atoms bouncing around of an object that is higher temperature, on average, those molecules have more kinetic energy than something with lower temperature. So if I take an object with a higher temperature and a higher average kinetic energy of those little molecules, and I have it come in contact with something with lower temperature, on average, the collisions of the higher temperature molecules will transfer energy towards the lower kinetic energy molecules. And so in general, you have transfer of this average molecular kinetic energy from the high temperature to the low temperature. That's heat. Heat really is a transfer of very localized energy from the molecules, from their random motion, to something else. And that's why heat generally requires conduction or convection or some sort of contact, right? You have to have some sort of fluid coming in contact with your hot object or cold object, or you have to have something solid in contact with the hot object, cold object, right? And the heat transfers really at that surface. And then it kind of works its way in, right? When I was very young, when I was like 4, my mom would always tell me to drink the soup on the outside of the bowl. Because if it's hot, if you drink from the outside of the bowl is cooling faster than the inside of the bowl. And so you'll get the cooler soup when you drink from the edge. Life lessons. So, but that's basically the same idea though, is that if your fluid or your object is hot, it will cool faster on the outside than the inside, right? And that's heat. Okay, so heat is the transfer of this thermal energy, and thermal energy is the random motion of the molecule. So, thermal energy is the average. I'm gonna say motional energy. I want to say kinetic energy because it can be from the random motion, it could be the vibration, it could be rotation. There are many different modes in which energy can be stored in the atoms or molecules, but it's the average motional energy at the molecular level.
Can we relate this to velocity and momentum?
You can. You can actually, it's an entire field called kinetic theory of gases, which is in chapter 17 of the book, I think. 16, a macroscopic description of matter. And then, sorry, not 17. You start getting into thermodynamics. Where is it? I think it's chapter 18. Yeah. You start getting into this thing called the kinetic theory of gases. And basically, if you spend a lot of time being very careful about the math of you take a molecule or an atom, treat it like a billiard ball, and have it bounce around, and then you kind of look at how it bounces off different particles, and then you do that for like a statistical model of like a trillion, billion, whatever molecules. You start getting a model of kind of how temperature is a measure of the energy on the inside. And actually, there's a lot of really important conclusions from that. You start looking at how molecules tend to arrange themselves too, which leads to a measure of entropy. Entropy, you probably learn in chemistry that entropy is like the measure of the randomness. It sort of is. It sort of is. There's a direct relationship between the temperature and entropy of objects. Okay, so thermal energy, well, you can think of whatever example here, hot coffee, whatever. Right? Okay, so that's thermal energy. So when I pointed at the mechanical energy, you can count elastic energy as a mechanical energy. You can count gravitational potential energy as a mechanical energy. Mechanical energy is just any kind of energy associated with the bulk physical features of an object. Okay, so like, is it moving? Is it falling? Is it stretching? Is it waving around? So it's a little different from like electrical or chemical, right? It's not really the bulk. Some of these other things are not the bulk object. Okay. Lastly, we'll get to wave and electromagnetic later. Let's deal with nuclear, and then we can move on. Okay. So what's nuclear energy? What's nuclear energy? How would you define it? Sure, Joe.
Maybe the strong force holding the protons and neutrons together.
Not just the strong force. I mean, I'd say both the strong and weak force, right? Because they're both involved in the holding of. So strong force holds your protons, your neutrons together, and so on and so forth. But your weak force is kind of your decay of your protons and neutrons, right? So really a combination of both. But let's be. I don't want to introduce more vocabulary to define this one. Then we'll have to talk about what the strong and weak forces. So generally speaking, when you talk about nuclear energy, is the energy stored in what? What kind of bonds? Subatomic. I guess it really is kind of hard to describe it without using strong and weak force, but I guess if we were to, if chemical energy is in the electrons, then nuclear energy is in the nucleus. I mean, I think that's really the easiest way to describe it is energy stored. Let's generalize it a little bit. Stored in the bonds in the nucleus of atoms. Energy stored in the bonds. So different kinds of bonds, if you really get into the subatomic, looking at the insides of protons and neutrons, and you start looking at how the nucleus can decay, you know, you have that stuff too. Okay, so this is a very qualitative look at energy. Okay, and when we look at energy, there's a couple of really important concepts regarding how we treat energy. First, we measure energy. Here, I'm going to do a kind of a break. We'll do a little bit of a break. Okay, so we have our list of different kinds of energies. I know I left out electromagnetic and wave. We're going to hit those later on in the year. We don't really hit up thermal or nuclear, so, all right. When we measure energy, energy is measured in joules. Named after a guy. So 1 joule is equal to 1 Newton times per meter. Or not per meter, 1 Newton meter. So this is going to be kind of confusing because torque was also measured Newton meters. So you really have to look at the context of the situation. Okay, so the context of the situation will tell you whether you're talking about a joule or if you're talking about a Newton meter. But they're not interchangeable. I mean, torque and energy are not interchangeable. You would never describe the torque of an object, torque on an object in joules. And you would never, although you can talk about the energy of an object in Newton meters. So be mindful about that. So when you talk about energy, it's really important to describe a system versus its environment. Okay, so when you look at I'm just going to draw a little diagram here, a little box, and here's your system, here's your environment. Okay, kind of like how we talk about momentum, you can have a system and its environment. So you have external forces. In the same way, when you talk about a system and its environment, the environment is external to the system. So your system can have a certain amount of energy in it. Your environment is usually considered to be an infinite reservoir for energy. It can remove as much energy as you need. It can provide as much energy as you need. Generally speaking, you kind of treat your environment like it's just there, it doesn't matter. Right? Your system is what you're concerned about. And so when you have energy transfer, right, you can have energy transfer into your system or out of your system. And a really important concept about energy is that energy is conserved. You cannot create or destroy energy the same way you can't, generally speaking, create or destroy mass or matter. Okay, I mean, we now know that we can, but there's actually an equivalence between energy and mass. And so when you destroy mass, it actually turns into energy. So really, you can say it's all conserved anyway. Okay, so what that means is, and I'm putting a question mark here because it's just a matter of, are you transferring energy or not? If there's no energy transfer between a system and its environment, then usually you say that the system is isolated. And if the energy is, if the system is isolated, and you don't have any energy transferring in or out, you should have a constant amount of energy in your system. Okay, so in other words, if we were to define the law of conservation of energy, okay, if no energy transfers in or out of your system, the energy in the system should stay the same. Okay. The same thing with momentum, right? If you have no external forces, acting on your system, your momentum will stay constant. And so in the same way, if there's no energy transferring, in or out, no external energy sources, right? Okay, so this is maybe a good one to kind of think of an example, right? So what is an example of give me an example of an isolated system. It's kind of hard. What might be an example of an isolated system? A system that does not transfer energy in or out with its surroundings.
Something in a vacuum.
Something in a vacuum. Okay, so usually that's the case. So actually, if you look at some of these cups, they are or like double paned windows. There's a gap between the two sides, the inside and the outside, and usually you have a vacuum. You try and have it as a vacuum so that there's no way for the heat to transfer. Okay, we already said that thermal energy is your molecules bumping into, or molecules moving at a certain speed. When they bump into other molecules, they transfer energy. If there's no molecules on the other side, if it's a vacuum, then the molecules can't bump into anything. Which is kind of why, if you look at a vehicle in space, it's very hard for something in space to actually cool down. Because it can't just cool down from convection or conduction. It has to radiate the heat. And that's actually a pretty slow process most of the time. Yeah, a vacuum is kind of a good way to try and isolate a system. Any other ideas? How about a non-isolated system? Or, yeah. What's an example of a non-isolated system? Sure.
A bowl of soup on a table.
Perfect. Bowl of soup on the table, right? So does the energy transfer in or out? Usually if it's a hot soup. Right? If it's a hot soup, yeah, energy will transfer out. It will transfer out until it reaches thermal equilibrium. Thermal equilibrium is when they're at the same temperature. Same temperature means the average molecules have the same speed. And so then when they bounce around, on average, there's no exchange of energy, right? Cool. All right. Questions about this stuff? Just really a first look at energy. Everything that we talk about from here on is going to be looking at very specific cases of energy. But I wanted to visit this because when you look at the conceptual questions, or at least just, I think energy in particular is really important to have a big picture about, even if it's not on the AP Physics C exam. I feel like your generation is the generation that's going to have to think about energy the most. Did you guys watch that, what was it, the National Geographic video with movie with Leonardo DiCaprio? He did this movie, and I think it's on YouTube, you can watch it, but it's kind of like another documentary on climate change. It's really good. Kind of like when I was growing up in high school and Al Gore came out with An Inconvenient Truth. It's like your generation's Inconvenient Truth. It's really good. You should look it up. I can't remember. I think it's called Before the Flood or something like that. And it has some pretty compelling video. There's a spot in Greenland that he goes to visit, and there's this weather machine with like a 18-foot tube that's meant to be dug down under the ice to kind of get a measure of the temperature. And so much of the ice had melted away in the last 5 years that the whole 18-foot tube was no longer under ice. It was originally under ice 5 years ago. It is no longer under ice. So that's not just like a hole. It's like the entire, thousands of square miles around it had melted down 18 feet so that there was no more any ice around it. So the tube, it all just became dug out because there was no ice around it. That's how crazy climate change is. And so it's really interesting. I think it also has a pretty informative view or discussion about what China is trying to do about climate change, what India is trying to do about climate change, because between the United States, China, and India being either extremely populated or extreme contributors to, pollution, it's a lot there. Okay, so that is all conceptual stuff. Let's get to some of the math. Okay, so that we can actually, some of the stuff that you'll need to know for the unit. Okay, we need to define something called work. Okay, what I'm gonna do is I'm gonna do some math tricks here. It's not really a trick, but we're gonna be doing some calculus, and it may be kind of hard to follow if you haven't already taken all the way through Calc AV, but just try your best. Once again, just like with momentum, this all comes down to Newton's second law. F net equals to ma. Okay, we'll start with that. Okay, and from here we can say that, well, your acceleration, let's do that in terms of velocity, we'll say that your net force leads to your mass times your rate of change of velocity. Okay, that's what acceleration is. That's the definition of acceleration. Well, with momentum, what we did was we tried to investigate what forces do over time, right? And that really leads to an impulse. If you look at all the contributions of a force over little slices of time, you get what the impulse is, you kind of get the net change in momentum. We're going to approach it a different way. I'm going to write it like this. What I'm doing is I'm saying, well, as your velocity is changing, if you change position, there must be a relationship between how your velocity is changing based on where you are at and where you are at with respect to time. So that's what this is, and I'm going to do this. This trick here is called the chain rule. Okay.
We just did that last class.
All right. So this is the chain rule. If you haven't seen the chain rule before, what it means is you kind of look at how dv, dx, dx, dt, you kind of have a chain like this. It's not so much that the dx's cancel. It's more that if you can show that if you look at how your velocity changes, guys, you can show that if you look at how your velocity changes with position and then how your position changes with time, and their product is equivalent to the rate at which your velocity changes with time, you kind of introduce a intermediary variable, so to speak. Okay, so this is very interesting because if you look at this, what is dx dt? Good. Change in x over change in time, change in position versus change in time. We have a variable that usually represents that. We can actually pull, this is v. So I have f net equals to mv dv dx. Okay. From here, what I'm going to do is I'm going to look at how I'm going to bring this over. I'm going to have f net dx equals to mv dv. Okay. So by taking my net force and looking at its contribution over a set of positions, what I find that it should be related to how my, I guess you can say it's your momentum over a set of different velocities, how it's changing over a set of velocities. But as we do that, I don't know if that's really the best way to interpret this. The left-hand side, it kind of makes sense to interpret it that way. I think the right-hand side, not so much. But let's go ahead and integrate and actually look at the outcome that we get. So I'm going to integrate the left-hand side. See, now your net force can be a function of your position, but it might not. Okay, so what this is saying is that if you had some sort of object moving along, like if I'm pushing a desk or I'm pushing a table and I apply a force to it, and I added up and I created a net force versus position graph, and it looks something like this, and I add up the area under that, right? Remember, the integral is just looking at the area under that graph, F net times x, because I'm looking at these little, individual little squares, right? Or rectangles, sorry. This is kind of unresolved. You can't actually calculate what that that integral is because you don't know necessarily what this function looks like. On the right-hand side, though, if your mass is constant, v dv is always integrable because it is a variable chopping up itself, so to speak. So you can actually integrate this one, and you actually get this. I guess you can write it like you have 1/2, right? Cal people, the integral, it's the integral of x dx, right? So if you're wondering how I got this, here's mathematically what an integral does. In terms of the trick is an integral. Actually, Calc AB people, have you guys done derivatives yet?
Yeah.
Okay, you guys have done derivatives. So it is essentially an antiderivative. It is how you get back, you undo a derivative, so to speak. So in other words, if I were to ask you the derivative of what gives you x, right? That's what the integral is. The derivative of what expression gives you x, right? Then you can say that that would be 1/2 x squared. Right? If you think that through, when you take the derivative of x squared, you get 2x. The 2 cancels with the 1/2, that gives you the x. So in the same way, if the mass is constant, it doesn't influence your derivative in the same way it doesn't influence your integral. And so you're essentially just taking the antiderivative of v, which is 1/2 x squared, or in this case, 1/2 v squared. The important thing about integrals, though, is that, again, you got to remember you're adding up a bunch of area, right? So when you add it up, you need to have some sort of beginning spot to final spot for which you're adding up the space under that graph. And so you can say that this is like a change in 1/2 mv squared. Okay, so that's the right-hand side. Yes?
What are the F and I?
F and I is like initial, final.
Oh,
Yeah. And if you're, so this is an integral notation, meaning you're taking, you're taking the difference from the final position from the initial position, which is essentially just your change. This is your change. So we will call this right-hand side your change in kinetic energy. Actually, I can't remember how the book uses. It just uses K. Sorry, I'll just pick that. I want to stick with the book's notation. Delta K. Okay. This is the change in kinetic energy. Right? Have you guys seen this before? 1/2 mv squared, right? This is where 1/2 mv squared comes from. Okay. If you ever wondered, like, who came up with 1/2 mv squared? Why does it work? This is the mathematical derivation of kinetic energy. It's just looking at how your force, it comes from Newton's second law. The same way we got mv for momentum, that's the same thing for kinetic energy. We're just using Newton's second law and doing some math tricks to it. So that's the right-hand side. The left-hand side is this F net. Okay, And we will call this work. This is the mathematical definition of work. Okay? And in this case, this is actually the net work. The total amount of work done on an object is the net force acting on that object over a certain amount of positional change. And that will lead to a kinetic energy change. So in other words, if I consolidate this, your net work is equal to your net force over some distance will lead to a kinetic energy change. This is called the work kinetic energy theorem. There are a lot of implications here, okay? First, in order to do work, you must have a force that causes the object to move, okay? The object actually has to move. This force has to cause it to move, well, I guess, there's, okay, we'll get back to it, okay? It actually has to cause it to move. So if I just push on this ceramic table and it doesn't go anywhere, I'm not doing any work on it. Even though I can expend my own muscle energy and I can get tired pushing on it for a very long time, I'm not actually transferring any of my energy into the table, okay? So look at what it says. If I push on an object and cause it to move, I will cause it to change kinetic energy, which usually means I will cause it to change speed. So work is, by definition, an energy transfer. Okay? When I say I do work on an object, I am transferring energy to an object by changing its kinetic energy, therefore changing its mechanical energy or whatever. I'm transferring mechanical energy. Okay? And I'm doing so by applying a force. Okay. Any questions about this outcome? The meaning behind it? The meaning behind it is very much just pushing on something and actually causing it to move will lead to a kinetic energy change. Okay? Questions? What time are we out today? 33 or something? 35, 30 something. I think it's 33. For some reason that number makes sense in my head. Okay, well, when you push on an object, okay, now this is the net force. This is all the forces put together, right? But there could be multiple forces pushing on an object at the same time, okay? So if you want to look at the work done by a particular force, you have to do it this way. Okay. Notice that I can't say it's equal to the change in kinetic energy because only the net force and the net work can actually cause any actual kinetic energy change. Okay. Now the work done by a particular force looks like this. Okay, the integral of the vector f dot product with the vector x. Okay, so what does this mean? This is the vector positional change. Okay, and this is the vector force, and it's a dot product. Okay. Oh, yeah, sorry. It's the vector dot product. Okay, so a dot product, if you think, look, or if you can remember back to when I was talking about cross products looks at how two vectors are perpendicular to each other. Dot products look at how two vectors are parallel to each other. How are they aligned? So let me draw a diagram of this. Let's say I have a box, and I push on it like this. Here's F. Whoops, that's a vector. Sorry. Okay. Here's F. I push on this box at an angle. Okay. And then this box changes in position this way. Okay. Notice that not all my force is pushing in the direction that it actually moves. Some of my force pushes downward, and some of my force pushes sideways. The part of my force that pushes downward, that doesn't cause it to move up or down, is not doing any work to that object because it's not speeding up or down, right? It gains no kinetic energy up or down. It only moves sideways. So only this component actually is contributing to its movement. Okay, so yeah, I think this is fine. If this is theta, then the work would be F delta x cosine theta. Okay. This is kind of a simplified example here. There's a couple things that I'm doing that goes from here to here. First, this only works if F is constant. If your force is constant and your angle is constant, which is going to be most of the problems that you deal with, if your force is constant and your angle is constant, then pretty much you can simplify this derivative or this integral out. And then you can look at it as like a net change, which is really nice. Which is really nice. For the most part, we'll just deal with this. But this is the work done just by this force. Okay. Notice that this work done doesn't necessarily tell us what the kinetic energy change is because maybe there's friction in here too. And then you can look at what the work done by friction might be, right? And you can have all these different things. Maybe there's air resistance, whatever it is. As long as there's any forces along the direction of actual motion, okay, they will be doing work on your object. Yeah, yes. So you have newtons from force and then delta x in meters. So Newton meters. Okay. So work is measured in joules or Newton meters, right? You'll see all of this is Newton meters. Even this is Newton meters. When you look at 1/2 mv squared, you have kilogram times meters squared per second squared, which is the same as kilograms meters per second squared times meters. Right? So that's also a Newton meter. Right? So all these, or it's a joule, whatever. Right? So work is a joule, but work is a transfer of energy. Kinetic energy is measured in joules. It's a measure of motional energy, and this is how they're related. As you apply forces on an object that actually contribute to its movement, you can have positive work and you can have negative work. Okay? If friction is this way to the left, sorry. If you have friction to the left and it's moving to the right, the angle you can argue between them is 180 degrees. Right? The 180 degrees, which means that the dot product would be negative or something like that. Okay, so you can have negative work. You can have work that's taking energy out, like friction, and you can have forces that contribute to it. And then when you take them all into account, that the net work will equal to your kinetic energy. Okay, your kinetic energy change. Okay. Any questions about work? All right. Let's move on then to doing some practice with this. And then I'm gonna stop the recording. No questions? Questions? It's kind of hard to have questions when we're doing this conceptual stuff, I know. When we get to some of the problems, maybe